Good morning. In this class, I will cover a big topic, so I should say large topic, synthesis of bicyclic polyheteroatomic heterocycle. It is a vast area or vast sub area I should say, and in this topic I have selected only few important nuclei, namely one is indazole, then other could be sinolines, then third one is well known to many of you, is known as purines, and the fourth one is known as pteridines. So, I have selected only 4 of them under the category of bicyclic polyheteroatomic heterocycles, and before we start I think we should be able to know the structures. The first one, as the name says, it has to be a 6-membered and a 5-membered, and just like indole, so we can say 2 as a indole. So, this is indole. Sinolines also are very similar to indazoles, but the second ring is a 6-membered ring, and all of you know purine consists of a 5-membered ring and a 6-membered ring. 5-membered ring is fused with a 6-membered ring, and 5-membered ring is imidazole, and then the other one is pyrimidine. So, this is an important nucleus, all of us know, and then next most important is again a 6-membered fused with a 6-membered, but in this case you have a pyrimidine ring system, and then you have 2 nitrogens on these sides, and this is, so this is actually pteridines, this is pyridines, this is actually sinolines, and this is indazoles. And some of you probably also know a kind of a nucleus which is pretty familiar in organic chemistry. It is a 6-membered, again a 6-membered with pyrimidine nucleus, ketone up here and an NH2, okay. And this nucleus also is commonly encountered in heterocyclic chemistry. This is known as pterine. So, you have to know all these things, okay. These are very important nuclei. I mean most of them either biologically active or they are found somewhere in pharmaceutical formulations, and of course they are of continued research, means there are potential applications of all these nuclei. As we will go, we will see, and among these heterocycles, I think the third and fourth one also is important in terms of the nomenclatures, the numbering systems. I do not know how many of you know the numbering system. In case of purine, the numbering starts from a particular nitrogen. Unlike the conventional IUPAC numbering, these 2 systems will have a different kinds of numbering. They do not belong to these IUPAC rules, okay. And that is because of the historical reasons. Like say, I mean why naphthalene is naphthalene, it could have been benzobenzene or something like that, but historically it has been named as naphthalene, and that name has been retained by IUPAC. So, similarly, purine nucleus, all of us know many of the nucleic bases of nucleic acid bases would have this sort of nucleus, and the numbering starts from pyrimidine nitrogen, that means 6-membered and 1, and then it goes to 2 and 3, then this one 5, sorry 4, 5, 6, and then third nitrogen is 7th, 8th and 9th, okay. So, this is the you have to remember, nothing can be done, and then let us go to the other one. Other one is what? Pteridine. Pteridine also is a very important nucleus, as you will go, we will see, and in fact very briefly I can say pteridine is found in Anybody knows? Pteridine. Pteridine is found in this wings of the butterflies. So, this is the coloring material, actually it is pigment, it is due to this the pyridine nucleus. Okay. And it is in this case the numbering starts from here, this nitrogen. I mean there is no logic, but again it has been retained and it has been accepted. So, 1, 2, 3, 4 and 1, 2, 3, 4, 5, right. So, this should be 5 and this nitrogen is not numbered though. So, actually this carbon is numbered. So, then the 6, 7 and this. So, this is how the numbering goes, and this nucleus is also pretty important because of many important occurrence. For example, it is found in methotrexate. Methotrexate is nothing but it is a commercially available anti-cancer drug. So, likewise also it is all found in molybdenum cofactors, pretty important enzyme. So, that is there, like say pteridine for example, pteridine where do you find pteridine? Pteridine actually is found in spinach. Spinach is nothing but any kind of palm, fine. Okay. I should not say palang, any kind of okay. So, but there are, that means that they are important, as you will see, you will have more examples. Then also some chemical behavior also peculiar. For example, this pteridine is soluble in pentane or hexane as well as water. Normally those molecules which are all soluble in organic solvent are not soluble in inorganic solvent, etc., but in this case it is it's true. Okay, let us look at some of the synthetic aspects of let us say indazoles. Indazoles, I mean there are of course hypothetically one can write so many methods, so many approaches, but what the known approaches, all of them would start from disubstituted benzene derivatives, all of them. Okay. And there are about 6 or 7 methods, but today we will talk about only 2 of them, or rather maybe 3 of them. One of these ways is to start from isatin. I think all of us know now isatin is an indole kind of nucleus with 2 keto groups, 1 amide and this thing, you can start from there. The other that is also pretty popular, it is pretty interesting too also, it starts from orthotoluidine kind of thing, orthotoluidine. So, this is another way, and third approach again quite interesting. This is very interesting in the sense because this sort of topic is quite useful. So, this is I think by looking at the structure you can see that there is a when I write this the number the right one, it something should come to your mind. What is it? Any idea? Okay. So, but any case all the 3 will have, let us say, I mean sort of disubstituted benzene type of compounds. Likewise there are, I mean, so you can think about anything, for example you can think about corresponding let us say hydrazone and then do something to get to the compounds. Then you can also have nitrobenzaldehyde, orthonitropenzaldehyde. So, like these you can think about this, but all of them involve the 1-2 disubstituted compounds. Okay. And actually third one is important, as I said, it is a precursor of benzene. If you use let us say cesium fluoride or potassium fluoride or tetrabutyl ammonium fluoride, it first the fluoride attacks the TMS group and then it induces the loss of triplet. So, it is a nice important precursor at the room temperature. So, as we will see how to make use of it in the synthesis of indazoles. Okay. The one that is mechanistically important is the middle one, the second one, what you will see if a toluidine kind of molecule is treated with sodium nitrite in presence of acetic acid. So, acetic acid is basically solvent. So, one would expect, the expectation is pretty obvious, right, and so you will have a diazonium kind of salt, but this diazonium salt does not exist in that way. It is interestingly cyclizes to, as if it forms a negative charge here and then attacks the diazo group, and so you will have attacks the diazo group. So, you will have obviously this kind of intermediate, and that eventually tautomerizes to the indazole. So, this is quite interesting. That means, a diazo compound which is not believed to participate in intramolecular reaction. This is an intramolecular reactions of the diazo compound. Okay. Likewise, just one more example probably I can give you. Just one step you can get to this indazole derivative. For example, you begin with, again it is orthotoluidine, that means you will have to have a substituent here, and I think now so it is pretty similar. Only thing in this case NH is protected as AC, and then to carry out the reaction, all of you know what is the substitute of sodium nitrite in organic solvent. Substitute of sodium nitrite, that means nitrosating reagent in organic solvent. All of you know, you have studied in BSc. One of them is amyl nitrite, other one is butyl nitrite. So, in this case it is the one you have shown here, it is tertiary butyl nitrite. Okay, it is basically source of NO plus. So, it is equivalent to and in this case it is solvent I have missed, but the temperature required is around 90 degree centigrade, and as in analogy with the previous example, one can write this structure here is an N-acetyl indazole, and of course, E1, all of us know E1 stands for this methyl ester, right, in our case. So, like this you can I mean nicely get an access to these indazole derivatives. Okay, the second method that I would like to talk about, I think the one example is good enough to demonstrate the utility of isotin, right. If you recall, in one of the last classes we have talked about the use of isotin in the synthesis of, anybody remembers? Isotin is a very useful compound actually. There are so many multi-purpose uses of isotins, and in one of the classes we have talked about actually it is used in the synthesis of quinoline. The structure demands quinoline. So, quinoline synthesis. In this case, if you treat with paratoluene sulfonic acid and methyl formate, so I think all of us know what is the answer. It would, because there are two kinds of which are ketones, one is amide, other is the just ketones. So, it will undergo ketalization, right, it will undergo the ketalization. The next thing that is done is sodium hydride, and then one new reagent is used, that is called DPPONH2. What is it? It is nothing but it is a source of, this is equivalent to, you can say NH2 plus, like NH2Cl. So, similarly this is equivalent to NH2 plus. So, you can guess what is the possible reaction. There is only one abstractable hydrogen which is sitting at nitrogen. So, this would aminate this nitrogen, and you will have the ketal as it is, And by the way, you have to remember the structures also of this one. DPPNH2 is nothing but is a phosphenyl hydroxylamine. So, that means it has to be like this, and so diphenyl. So, that I think as the name says, it should be diphenyl, right. Diphenyl and third alphabet is phosphenyl, and this is O and hydroxyl amine. This is the structure. So, when a nucleophile attacks this nitrogen, this diphenyl phosphonate group is coming out as the leaving group. It is a pretty useful one. What is the next reaction? The next reactions one would expect is just if you boil with dilute sulfuric acid, in this one you can get a nice kind of rearrangement, and eventually it will give you this indazole with a carboxylic acid at the 3 position, carboxylic acid at the 3 position. Okay, I do not have to explain to you, right? Sorry, hydrogen is up here. I do not have to explain. Actually, under the acidic conditions, it undergoes what hydrolysis, right? So, hydrolysis would give you NH and basically phenyl hydrazine and a keto here and a carboxylic acid. So, just the hydrolysis of the ketal and hydrolysis of the amide, that will give you the, and then this one would undergo cyclizations to this. So, this is a nice I mean it is a clean kind of synthesis. Let me give you there are other kinds just in this context. Let me just quickly let you know an interesting reaction. I do not know whether you should be able to predict the product of this reaction. Let us say indole, all of us know, is a famous nucleus. Then this sodium nitrite also is a famous reagent, right, famous reagent. So, in the presence of acid you get a new compound. So, what could be the structure? Nitrosation, fine. Then what? NO plus, okay. So, presumably it will I mean it can indole, all of us know, it can undergo nitrosation at the 3 position or nitrogen. There are 2 possibilities, but with nitric acid it is a hard one. So, you can expect a N nitrosation, right, and then what? See, you have actually I should have written here dilute acid. So, that means you have water in it. So, if you actually enamine, if you hydrolyze enamine, the indole means basically enamine, right. If you hydrolyze, what you are expected to get is NH here and NO, and in this case what you will be getting here aldehyde. Enamine means hydrolysis would give you the corresponding starting metal, the corresponding secondary amine and the aldehyde or ketone. Now, you can guess in the previous example in compound with the previous example means in last slide I have shown that orthotoluidine, if you treat with sodium nitrite, it gives you the indazole. So, you have with an ester group there, you can end up with an ester pyrazole indazole. So, this would immediately cyclizes to it will cyclize to the indazole here, and then so basically you will get the 3-formyl indazole, just like the previous example. When you see this toluidine treated with sodium nitrite, it gives the indazole. Okay. So, then let us look at one more reaction. I think that would suffice for the synthesis of indazole. Like say, if you this is the benzene route, I think that is the way it should be known. benzyl. If you treat with fluorobenzene with TMS diazomethane. TMS diazomethane basically is a substitute of the diazomethane, and then LTMP in ether, and a reflux. Ether reflux means basically 35 degree centigrade, and in one step you will be getting this indazole derivative. So, indazole derivative, and here TMS is, so TMS indazole. By the way, recently I have come across a patent actually describing indazoles for the use of treatment of diabetics. Okay, that means they are pretty useful. Now, I think all of you know what does LTMP stands for. We talked about that in 4th year. Lithium tetramethyl piperidite, like LDA, lithium diisopropyl amide, IDE, so piperidite. Okay. So, it is basically a base, hindered base with this. What is the mechanism? Mechanism is it goes to benzene here, and then in the presence of the strong base you get the lithium, and this diazonium salt here, this is diazo compound, right. This is TMS. So, one can think about this electron movement to benzene as an electron acceptor, and this is neutralized, and then you have one hydrogen up here, and so it will now form this nucleus, sorry, double bond, and then TMS, and in the presence of the excess base it will form this this negative charge here, and then negative charge of course isomerizes to upon workup will give you this. Okay. So, this is a fairly okay method. That in the next example what I will see rather the most popular benzene precursor these days, what I have said before, the most popular one is the TMS here and O trifluoride. What does it do? If you treat with a fluoride reagent, so fluoride goes to TMS, and then trifluoride comes out. So, eventually you will be getting this sort of a neutral or the basic conditions benzene formation. Now, if you treat this with let us say R CHN2, apparently unless you know, you cannot think of this indazole formation. So, like the previous example here, under this under the condition you will be getting this indazole formation with NH here, double bond and R. And this is a pretty fairly general method, but the only condition that you have this, but it is condition sensitive. Condition sensitive means this is obtained if you have this potassium fluoride and of course 18C6 crown ether, 18C6 crown ether. So, if you use, then you will get this. Okay. But if you have a different kind, the same kind of substrate, but the reagent is little different, this is cesium fluoride, and which is supposed to generate more nucleophilic carbon ion, and the other condition is methyl cyanide, that is acetonitrile, and room temperature. What do you expect? You will expect a very similar compound, but not exactly the one we have seen we have been seeing in the right hand side. So, guess since we have been talking about these indazoles, we will be getting the indazoles here, and R will be R, and this N will be linked with something else. This is one of the serious byproducts in the reactions. Okay, or you can in fact you can get as the major product provided you monitor the reaction, or rather optimize the reaction. Okay. And what could be the byproduct? Guess. Just basically if you have little mechanistic approach, you can quickly come up with the byproduct you will be getting here. Nitrogen would be linked to a group. What could be? Phenyl. That means at the end you will have a nitrogen minus here, that minus will add to another benzene nucleus. Okay. That is how it will work. And let us go to the next one. Next one is cinolene, right? Cinolines. What is it? It is very similar to indazoles, but this second ring is a 6-membered ring with this. I think before that I should also tell you some of the other analogous nucleus. For example, did I do not know whether if I have told you or not, there is a nucleus for example like this, there are like this, there is a nucleus which will be looking like this, there is a nucleus which will, that means all these are basically diatomic bicyclic compounds and this. So, that means right, how many of you can recognize these 3 nuclei by name? They are on the right hand side. Cinonyl, you see it is 1,2 nitrogen. Okay. Any guess? This is an important nucleus again. Thalazine. Why? Because most of the phthalic acid will have a carbon up here, carbon up here, and it comes from hydrogen. So, phthalic acid by hydrogen. So, and many of you know thalazides are very useful. This luminol, have you heard of the term luminol? How many of you heard of have you heard of luminol? And it is a very important molecule. You can do it in the lab. As a nitro corresponding, I mean I roughly remember it said that is obtained from the corresponding phthalic anhydride, and nitro is somewhere here, it is a nitro. Why it is luminol? Because if you tautomerize, it is hydroxy here and hydroxy here. If you treat with hydrogen peroxide and little bit of iron, you know what happens? It is an example of chemiluminescence. Chemiluminescence, you can see the light, the fluorescence. Okay, you can do it. At least I have done it once when I was a graduate student. Okay, it persists for at least half a minute or a minute. You can see the nice luminescence. Okay, and so and then this one, what is the name? Okay, this is queen oxaline. Queen oxaline. Okay, and this one has a very similar name, quinazoline. Quinazoline. Okay, I do not know how to remember this one, but I can see that thalazine, because we have 2 carbons here like phthalic acid, and quinazoline, it has a way to remember. This portion comes from oxalic acid. There are these 2 carbons here. So, that way you can remember that actually it comes as quinazoline. So, that ox comes from probably there. And so, but today we will be talking about just as an example of the polyheteroatomic these cinolines. Cinolines of course will have the 1,2 nitrogens of this kind, and as usual they are found in many compounds with anti-tumor properties. And then there are some semiconducting material, for example, the one I am writing now has nice n-type semiconducting properties, this one. So, you have lot of phenyl here and there, a lot of phenyls. Okay. So, then of course, cinolene means you have to have nitrogen. So, 2 nitrogen, 1, 2 nitrogen here, and then phenyl up here. It is a symmetrical one, it is a symmetrical one linked with a benzene ring system. You do not have to write, just I mean see most of the aromatic compounds will have some material properties, electron optical properties, optoelectronic properties, okay, or conducting nature. Now how to make, our case is how to make it. One of the classical ways to get into this sort of or access this sort of material is ring expansion of indole again. In indole, now if you treat this with NH2Cl and nitrobenzene in the presence of heat, I think this is the first step and this is second step, and you can guess what happened. It first forms this again this N nitroso N amino, right, N amino, and then this is in enamine part. So, enamine part would the enamine part, and then that would hydrolyze to this hydrazine. So, this is basically one way of making the, like the previous example is an hydrazine here, and this is this aldehyde, Then that shift phase formation, aromatizations, all these things eventually will give you the phenol. So, this is one way of doing it. The other way is the other ways could be, this is quite interesting. What are the other possibilities? Again is disubstituted aniline derivative. So, or benzene derivative, you take up this one, then you have to have necessary carbon, that is it. So, what is the linkage here? That would permit the formation of the phenol nucleus. You see, you have to have 2 carbons and little bit of this unsaturation, because to comply with the oxidation level of the final product, right. And in this case it is this alkyne. See, throughout the heterocyclic chemistry, if we have a amine and a carbonyl, and if we do not have a carbonyl, then you substitute the carbonyl with an alkyne precursor. This is the quickest way of thinking heterocyclic synthesis. Okay. Now, this is so if this compound is treated with let us say nitrous acid, and maybe I mean let us say nitrous acid and heat probably, then quite interestingly, so what you will expect? You will expect, right. So, diazonium salt, and then although apparently these two are quite far apart, but it would cyclize to this nucleus. So, that means plus sign is here, this R, nitrogen, and this, and depending on this your reaction depending on the reaction condition, you can get OH here, but in this case you will be getting OH, in this OH, and if you have a concentrated nucleophile like chlorine, bromine, iodine. So, you can also have incorporation of this halogens here in the presence of the carbonium ion. So, these are the 2 ways of doing it, but the recent one could be just I think this in I do not have the reference, but it is published somewhere between 2010 and 2012. It is quite interesting. You start from this azo compound. So, azo compound, all of us know azo compounds are useful as what? Dyes, what else? Basically are dyes, in food dyes also. Most of the food dyes available in the market, they are actually azo compounds. So, now if you treat this with an alkyne, disubstituted alkyne, let us say R here, and in the presence of a rhodium catalyst. In this case, the rhodium catalyst is rhodium Cl2 dichlor, and then Cp star. Cp star, this is believed to be in dimeric state, and this is catalyzed. Then equivalent amount of oxidant is required. Often I think many of you know cupric acid is one of the cheapest or rather cheap oxidizing agents, and then something else. So, this see all these organometallic chemistry would involve a lot of actually optimization studies, formulations, but if you know the little bit of the mechanism, if you know the mechanism, you can come up with the right combinations. I mean a non-chemist can also do. So, chemistry is something like this, a non-chemist can also do something, but they will have to just do trial and error, but we do little bit of intelligently, right, judiciously. So, we use little intelligent guess. And what is the intelligent guess? The whole reaction conditions and the reagent conditions are missing one of the reagents, and can you guess what could be the reagent? Okay. Essential product is now the silonyls, right. So, here option R here, R here. What could be the missing reagent? I mean I have shown this hydrogen up here. So, this hydrogen has to be abstracted. Organometallic chemist people say that it is CH activation. See this is a very popular term these days. If you can do a CH activation, you are doing something great. Okay. But I am an organic chemist. So, what I look at as a simple electrophilic substitution reaction, Friedel-Crafts reactions only, but with the metal now. So, rhodium you have a chloride, Friedel-Crafts reaction you have alkyl chloride, in this case you have a rhodium chloride. So, and but in this alkyl chloride can be activated by aluminum chloride, but rhodium chloride can be activated by, guess, no guess, silver tetrafluoride. All of us know it can pull the chlorine. Silver has a strong affinity towards chlorine and halogens. So, it pulls the chlorine, so rhodium plus. That means eventually what you will be getting here, you will be as an intermediate you will be getting an organorhodium, right, organorhodium, and that would be having a halogen here, right, but then you have a second nitrogen that can also displace the intramolecularly. So, one halogen is replaced by benzene nucleus, other halogen is replaced by nitrogen, and then what is left? Cp star left. So, this is this intermediate. Now, you have an organometallic rhodium complex, then all of us know that you have organometallics, you have the pi x, okay. So, there is a pi complex formation. Then once you have pi complex formation, oxidative addition, reductive elimination, so all these processes would proceed. Then eventually you have cupric acetate that would oxidize the rhodium again, and then you will enter into the catalytic cycle. So, eventually you will get to this one, and this is a pretty general one. Actually what happens in between when the reaction is over or rather towards the penultimate stage. So, what you will be getting here R and this is xenolinium salt here, xenolinium salt, because you have a tertiary butyl group. Then all of us know these tertiary butyl groups are because of the carbonium stability, it will be lost as a isobutylene, or if you have, let us say we do not have the enough chloride. So, you will have if you had enough chloride, you would have obtained tertiary butyl chloride, right. So, that means you will get the xenolinium. Now, how do you know this is the mechanism operating? Very simple, very simple. To test this, what you can do, just change the substrate. Here you will have just take instead of the tertiary butyl group, you take phenyl, and the reaction same reaction conditions, right. So, what you would be expecting now xenolinium salt here, you will be expecting xenolinium salt, but the phenyl group here, that is it, and the corresponding the counterand, in this case there may be this tetrafluoride. Okay, and this is R here, R here, R here. So, this is a kind of test, that means the tertiary that xenolinium salt is first formed, and then separately in one case if you have a methyl, for example, if you have very similar compound with methyl here, then you will be getting the corresponding methyl salt, right. rest remains as it is, and you will get this methyl salt here, but and that can be simply I think just heated with pyridine at 140 degree centigrade. So, you can get the demethylation done, and so pyridine attacking this methyl group here, neutralizing the nitrogen. So, you will get the free phenolines, So, these are pretty useful ones. Actually, this work is patterned after a scientist named, many of you probably know, any of you have heard of this person, Fagnow. He is a Canadian scientist, organic chemist, and very unfortunate. He died at the age of 35. He published so many JACS papers before 35, and people are thinking that he would be a really good scientist, but he died at the age of 35 or 40 maybe, below 40 for sure, because of anybody knows this story? Swine flu. Have you heard of swine flu? Tummy flu, swine flu, swine flu a few years ago it was in the news, swine flu. Okay. And so, let us talk about a bit of purine. So, purine, let us say, how do you let us say purine, all of us know it is an imidazole and pyrimidine. We have to remember also the numbering, right. You have to by the way, you have to at least purine, pyridine you can forget about, but purine you have to remember. For pyridine, for purine you have to remember the numbering system. And so, how can we make it, and what is the starting point? The starting point here, if you remember, this is 1, this is 2. You have to look at C2. C2 and C8. What does it tell you? So, this is how you actually, whenever you start with an heterocyclic molecule, you have to look at the structural features first. Structural features. Do you see any pattern? Do you see any similarity? Do you see any similarity between the C2 carbon and an existing starting material, or rather popular starting material? If you remember, in the first few classes in organic synthesis, I talk about only oxidation, reduction, this thing, that thing, and at the end of 4th year sample, only we have learned oxidation, reduction. That is fine, but that is a very important guideline though, a very powerful guideline for any synthetic chemist. Okay. So, do you see any similarity between the C2 carbon and with any particular starting material? Let us say, what are the starting material you can think of? Methanol, ethanol, 1 carbon, right, 1 carbon synthon, so called synthon, methanol, formaldehyde, formic acid, all these things, right, and all these actually, but if you see at C2 actually it has some resemblance with formic acid, right, or formaldehyde, formic acid. If you just take it out, because see basically this one, instead of nitrogen you put oxygen here. In this case, so it is formic acid. Take this carbon out. Instead of the nitrogen you put oxygen here, and in the place of nitrogen you put this here. So, that means the C2 matches the oxidation level of formic acid, and similarly C8 also matches the level of oxidation level of the formic acid. That means, one of the important starting materials could be, that means you have a CH up here and the 2 heteroatoms. Okay. So, this can be obtained from formic acid or the corresponding derivatives. This also can be formic acid derivatives. And by the way, historically if you see, if you take formamide, and I did not get this, I mean maybe you have to work it out, you can get, just simply heat it, you get the purine. It is a nice way of looking at this purine synthesis. The other approaches could be, there are 2 approaches. Now, you can let us say there are 2 approaches. One could be just you start with the imidazole, right, imidazole, and the corresponding disubstituted imidazole, The other could be disubstitutable pyrimidine, that is it. So, these are the two ways, these are the two ways. Now, how do you real life, how do you do? Let us say if you treat with simply treat with acetic anhydride, you will get it is a methyl substituted purine, and mechanistically basically Schiff's base condensation. So, likewise I will give you an example of here, let us say in this case in this case it should be, if you break this it would be NH2 here, and this one could be N like this, right. Okay. And to give another example, I think just quickly I just write example on this system. You take imidazole, and let us say if you have cyano here, and then NH2 instead of the imine there, sorry I made a mistake here, this is 5 member ring and double bond up here, and then of course, what I said C2 is equivalent to formic acid. In this case if you use formamide, so you will get the substituted purine, right. You have an extra amine group that would incorporate one NH2 group here, okay, this sorry, this I think we made a mistake somewhere here, oh okay. Sorry, I think the starting material is something wrong. Just correct the starting material. This should be amine here and the methyl group here. So, you have a methyl group, the nitrogen and this. Basically, I mean, so easy to remember. There are two ways to remember. You start with imidazole 1 and this, and either you break at. In fact, these days if you can also come up with this starting material very easily. How do you just write the structure in ChemDraw, use delete. Once you put delete, automatically you will generate these sort of structures. Okay. So, that is and last item that is to be talked about, let us say I will write the structure, right. You have to tell me the name. The structure, the heterocyclic nucleus that is here is NH2. What is the heterocyclic nucleus? The way I have written, any guess? To start with, I have told you in the very first slide. What is the heterocycle? Terene. It is called terene, right? It is called terene. Fine. Okay. So, terene, and then it has a name. I think many of you have studied medicinal chemistry or PABA, right? PABA, para-amino benzoic acid, and then this one let us see how many of you know this amino acid. Glutamic acid. So, I think all of you know glutamic acid, right? Okay. And so, that means you have three important components, and what is the name of the whole molecule? Folic acid. And what is it used for? Actually, it's very vitamin is very important actually. B12 or B complex? B complex. B9, okay, fine. But if you have this deficiency of folic acid, actually you will have lot of complications. I mean, I have a list. I think I can tell you. I am going to read out. It can lead to diarrhea. It can lead to anemia. It can lead to shortness of breath. No, it's important though. Important. Many of you probably do not know, but at least I had been benefited because of I mean prescription by a doctor. Okay, and I was having a deficiency of vitamin D, but many doctors said no, you have blood sugar. Then one skin specialist said no, you might be having a vitamin D deficiency. I was treated. I mean, I recovered in just in a week's time, while I suffered for 2 years before that. Okay. So, that means these are all I mean important areas. Okay. How do you make it? So, now how do you make it? Once again it is you just look at the structure here. So, pterine nucleus is obtainable from the corresponding amine, and so like say in this case diamine here, right, and this other portion all of us know this is a basically peptide derivative, we can say peptide derivative. So, you have all these things, and this is amine here, and in the middle you can see now we are organic chemist, we can think about, right, instead of, but you have to differentiate these two nitrogens. These, see, when you break down this folic acid, you will have it this nitrogen and this nitrogen. Between the two, if you just apply your nucleophilicity knowledge, acidity knowledge, all these resonance, all these things, one of them is more nucleophilic. Which one is more nucleophilic? Guess. Between the two underlined NH2 group, top or bottom one? Top or bottom? Of course, answer could be either top or bottom, but what you see here, right. So, that means the lone pair is now directed towards the carbonyl, that means this is not available, the top one is available. So, you put a carbonyl there, that is it, carbonyl there, CH2Cl, and then but you have to differentiate here also. How do you differentiate? Put two carbon, two chlorine atoms. All of us know Gem chlorine is equivalent to an aldehyde. So, that way just that is it. And by the way, this reaction is so easy to carry out, just pH 4 to 5, and this is an antioxidant, you can say, because it stops the oxidations, sodium bisulfite, just heat it, you get folic acid. So, that means with proper design one can do this folic acid synthesis very easily. And the last one, this is an important topic though, many of you probably have heard of Flavin, right. What is it? Flavin is again a pteridine derivative. So, it is a benzoterivate derivative, okay, and that means it is nitrogen up here, that means, okay, and then this portion is basically pteridine derivative, this NH here carbonyl, and then this, and I am just writing only one specific one because this is pretty useful. So, this is chloride minus. This has been prepared in very recently, very recently, okay. And what is used for? So, actually it is a nice catalyst for oxidation. Suppose you begin with an aldehyde, so you use this cat, that means it is a catalytic amount, and what else? I mean to get to the carboxylic acid, and it has been applied to many compounds, compounds. Okay. This is published in, so it is called Flavian catalyzed oxidation. It is a kind of a green catalyst. We have hydrogen peroxide, which is green reagent. There is no metal here, right? There is no metal here. This has been published in 2012. There are other papers, but latest one is this one. So, you can go to it and see, it is quite interesting, And so, what you have to do, you have to just use 1.5 equivalent of hydrogen peroxide, not much, 1.5 equivalent of hydrogen peroxide, and probably you have to heat it at some temperature. Oh yes, you have to heat it at 85 degree centigrade, and the catalyst amount that is required is very little, only this one, okay, only 2.5 mole %. So, you can go to this. And what is the intermediate? Intermediate is basically I think I will just write only the part structure. Hydrogen peroxide undergoes nucleophilic addition first. Nucleophilic addition first to get this hydroperoxide. Now, this hydroperoxide goes to react with aldehyde to form hemiacetal. So, hydrogen peroxide and let us say R prime. Okay. That means this one. So, this portion is R prime, and then all of us know that under this since peroxyl linkages are weak linkages. So, it removes this. So, oxidation done again, okay. And then it can be under the reaction conditions, it can be recycled to the corresponding chloride. The reaction condition, that is basically this HCl. And how to, but our topic, so this is a nice example of heterocycle being used as a catalyst for the oxidation of organic compounds. And how to make it, again do the simplifications. You start from alloxan. Actually this portion actually comes from alloxan, I think so, let us say, yes, alloxan. Alloxan actually it comes from barbituric acid or barbituric acid. Some people say barbituric acid. What is barbituric acid? Anybody knows? How do you make it? Barbituric acid is a condensation product of diethyl malonate and urea. So, if you oxidize that, if you oxidize with chromium trioxide, you will go to this compound. Okay. So, I think that is all about we have to talk about. So, what are the things you have to remember though? Summary of the class. First of all, you have to remember the structure of the important nucleus. Indazole is easy to remember because 1, 2 nitrogen. So, likewise quinolines, quinolines, all these things, they are pretty typical and pretty well known heterocyclic molecules. Then between the purine and pteridine, you have to remember at least the numbering system of the purine, because it occurs in many places, right. All these nucleic acid, most of the nucleic acid bases will have purine nucleus. Okay. Pteridine is important because of folic acid and what else, and the presence in the anti-cancer drug methotrexate, and of course, pteridine also is found in flavins, right, flavins. And then you have to make a difference between flavin and flavone though. There is a very commonly used word called flavone. How many of you know what is flavone? Flavone, Flavone. Green tea, people say green tea is having flavone nucleus. Anybody knows what is chromone? Chromone is something like this. And chromone, it could be of many kinds, right. Chromones, it can be of many kinds like this, right. Flavone is nothing but, if I have forgotten, okay, I think it is in 2 position or 3, that it may be on this side also, sorry, okay. It is a phenyl chromone, they are flavone, okay, pretty